So let's see, we have a question here from Hannah. Can you tell us anything about the history of quantum mechanics? Well, 1925 was sort of a big year for quantum mechanics. So we're heading for the centenary of what was sort of the year of the creation of quantum mechanics. But let's tell a bit more of the story. So the idea that things could be discrete in the world is an idea that existed from antiquity. This was people like Democritus, the Epicureans. They were all, the world is made of atoms. They had the really good idea that everything we see could be made of different arrangements of the same kind of thing. So that was sort of a first kind of notion. Then there was, for a long time, discussion, is light discrete or continuous? The first sort of, I would say, the big kind of by the 1800s, things were kind of, okay, we've really got to figure out, are things discrete or continuous, particularly for matter? And there was there was sort of two lines of development there. One was about chemistry and about observing that there were sort of integer multiples of different amounts of material that occurred, and that sort of suggested that things like water might be two hydrogens and one oxygen, rather than a continuous amount of hydrogen, a continuous amount of oxygen type thing. The other was work on thermodynamics, on the characteristics of heat, the question of what heat was, and the question of whether heat was somehow associated with microscopic motion or whatever else of discrete molecules. And the big person who pushed that was Ludwig Boltzmann. This is 1860s, 1870s, was kind of, yes, this is a way of understanding thermodynamics. And he had a whole kind of development of sort of an atomic-based theory of how that kind of thing worked. It was also picked up by people like James Clerk Maxwell and so on. But people didn't generally believe it. Even though there was a bunch of mathematics that got worked out about thermodynamics and so on, that was based on kind of this atomic theory of gases, it was generally, but really we know that heat is this continuous fluid, and really we don't have to have the atomic hypothesis for matter. And that whole thing continued basically until about 1900. And one of the things that had happened by that time was, well, Boltzmann had worked out a bunch of things about what would happen in different kinds of systems if one approximated energy as coming in discrete lumps. And that was but he only did that as sort of a mathematical convenience. Okay, then one of the obsessions of the 1800s had been to prove the second law of the thermodynamics, to prove that it was an inevitable consequence of the laws of mechanics that systems with large number of molecules and things would, even if they started off in an orderly fashion, would become more and more disordered over time. But there was just no success. There were lots of kind of interesting things developed, but there was no kind of slam dunk success in proving that fact. From the laws of mechanics determine the laws of thermodynamics. And for Boltzmann, that was through the atomic theory. Not everybody believed that theory, but that was the leading way to sort of imagine going from mechanics to the second law of thermodynamics. I will say, in a sort of, well, maybe more than footnote to this history, I myself have been sort of interested in the second law of thermodynamics for more than 50 years now. And I think I finally understand how it really works. It's a whole story about computation and so on, but that's taking us off the track of talking about the history of quantum mechanics. So back to the history of quantum mechanics. So there was this theories of heat and so on, big interest in proving the second law of thermodynamics. Okay, so along comes a chap called Max Planck, who was a pretty kind of mainline thermodynamicist, German thermodynamicist in the late 1800s. And one of the things that had been observed was this notion of radiant heat. So heat, you heat a thing up, a bar of iron or something, and it's hot, like red hot, for example. But then people had noticed that heat could be transferred radiantly. So that red hot bar of iron, just by the very fact that it's red hot, it was radiating something that could heat other things. There was some way in which heat could be radiated. And that notion of what radiant heat was a big mess. So people imagined that heat was this thing they called caloric fluid, which was some kind of fluid that suffused substances and led to them being hot. And to account for radiant heat, they had to have all these things about how it's a radiant form of caloric fluid, and it was a big, complicated mess. The thing that was surprising was, even though kind of the description of what was going on with radiant, caloric, and other things was nonsense, the mathematics that came out was perfectly adequate. And in fact, pretty much the same mathematics that comes out once you have a more correct theory of what these underlying constructs really are. Well, so by 1900, there had been a bunch of experiments done on so-called black body radiation. And what that is you have just an oven or something, and it's all coated, it's all black inside, and you heat it up. And somehow there ends up being radiant heat inside your oven. And the question is, what is that like? And the thing that was most notable was the frequency spectrum of what was generated. So, you heated your oven up to, I don't know what, let's say 500 Kelvin, something like that, 200 degrees centigrade, something like this. You would be able to detect that there was electromagnetic radiation of a certain frequency in your oven, that there will be a certain distribution of energies of distribution of frequencies of what was coming out of the oven. So you could heat it up so much that it got red hot, white hot, blue hot. You would get this spectrum of frequencies of light or infrared or something in your oven. Okay, the question was, what was that spectrum? And one thing one could do is to say, well, that's produced by the heat in the walls of the oven is sort of somehow interacting with the electromagnetic field, because people knew about the electromagnetic field. That had been something that from Faraday to Maxwell, it was quite well established that there was this electromagnetic field that could be described as this amount of electric field, this amount of magnetic field. Light was understood to be this kind of oscillating amounts of electric and magnetic field that had been predicted by Maxwell's equations from the 1880s and 1870s. And then Heinrich Hertz had said, well, if that's the case, it should be possible to generate a traveling electromagnetic wave just by having like a spark would generate some electromagnetic radiation that could propagate through free space, just like light propagates through free space. So he tried this. This is Hertz. And he tried this, and needless to say, he managed to get something where he had a spark generating electromagnetic radiation, and he could pick up some signal from that electromagnetic radiation somewhere else. People asked him, why are you doing this? It's, what's it going to be useful for? He said, well, it's just sort of basic research about Maxwell's equations. Of course, what he had invented was what became radio. And this idea that you could have an electrical effect that produced electromagnetic radiation that could propagate to somewhere else, that's radio. And that was invented, I think, in the mid-1880s. So that was kind of a known thing, that there was electromagnetic radiation. There was kind of that you get different frequencies of electromagnetic radiation from radio down to light and infrared and so on. And the question was, how much of that will be generated by the hot heat in a substance? Well, heat in a substance, if it was caloric fluid, and somehow the caloric fluid had to turn into radiant caloric, and there were various theories about how that worked. But one of the things that was a kind of an idea was that there was some kind of little oscillators in, this was the thing, by the time you thought that the material was made of atoms, but even if you just said there's an oscillator, because people knew that it was kind of like Hertz's spark gap was kind of like, so you put something electrical in somewhere and you pulse it in some way and it will produce this electromagnetic wave. So the idea was that somehow in this material, there were lots of little oscillators producing radiant caloric, producing electromagnetic radiation. Well, people tried to make that work, and there was a prediction about the form of the frequency spectrum. The prediction was wrong. The prediction was not what was observed. And around 1900, I think Gustav Kirchhoff, had made some pretty detailed measurements of the spectrum. And one day, Max Planck, as I say, mainline thermodynamicist, who believed in caloric fluid, all those kinds of things, realized that if you just took Boltzmann's mathematical calculation of what would happen with discrete packets of energy, and you use that to try and compute what you would expect the spectrum of electromagnetic radiation in a black body spectrum to be, well, you got the right answer. And so he fit those curves, and there was a parameter in those curves that he called lowercase h that appears in this distribution, and it's kind of the size of the quantum of energy associated with the electromagnetic field. And so that was, he said, well, we're going to introduce this parameter. He computed its value based on Kirchhoff's experiments. He got roughly 6.5 times 10 to the minus 34 joule seconds, I think. And that constant, that lowercase h, is now called Planck's constant. Its value is actually 6.6 times 10 to the minus 34 joule seconds, but he got it pretty close to right. And he just mentions that in this paper that he wrote in 1900. And that was kind of the place where there was the next piece of discreteness was being discovered. Sort of, well, there's probably discreteness in the electromagnetic field. But the idea that that was sort of associated with atoms and that everything was discrete, Planck didn't want to say that. Planck just said, well, there is this kind of formula that you can get by following Boltzmann's methods, and this is what it is, and it contains this quantity, lowercase h, that is sort of a measure of discreteness of energy, but he didn't really want to go quite all that way. Well, that was 1900, and so then 1905, well, actually 1904, Albert Einstein had been following this track that lots of people had been following to try and explain the second law of thermodynamics. And he had kind of this sort of logical, philosophical argument for the second law that involved kind of this thought experiment about doing this and doing that and so on. Thought experiment not super unlike what Sadi Carnot had done in 1824 when he first came up with things like the second law of thermodynamics, but this was a more advanced version of that. At that time, 1904, Einstein was in the tech industry, so to speak, in Switzerland at the patent office, and the sort of the high tech of its time was refrigeration. And so Einstein had been working on refrigerators, even made some patents about refrigerators himself. But so thinking about thermodynamics was sort of a natural thing to do. And the thought experiments he proposed were actually sort of refrigerator-related thought experiments. Unfortunately, they were not correct. They didn't explain the second law of thermodynamics. So his work in 1904 was really didn't really go anywhere. 1905, he kind of took the same kind of thinking, the same kind of logical philosophical thinking, which, by the way, Boltzmann had been a big enthusiast of. Boltzmann was still alive at that time. He died in, I think, 1906. But I don't think Boltzmann ever knew what had happened in what Einstein did. But Boltzmann himself had sort of given up on the atomic theory. He famously sort of said, one man cannot stand against the tide of history. And he said, I'm going to write down what I know about atomic theory so that, when people finally realize that's what's right, not everything will have to be rediscovered. Sadly, Boltzmann died, a couple of years after that, never knowing that very soon atomic theory will be reborn and the things that he worked out would indeed be highly relevant. But the 1905, Einstein worked on three things. He worked on relativity, he worked on Brownian motion, and he worked on the photoelectric effect. So the photoelectric effect, well, but Brownian motion was this phenomenon where little grains that were ejected from pollen had been observed by Robert Brown in 1833, I think, to under a microscope, you could see that those little grains were just getting kicked around. And nobody really knew what that phenomenon was. And Einstein, and I think slightly before him, Smoluchowski, had said, well, that's probably actual water molecules kicking these pollen grains. And then they had tried to do a calculation of that, and it had worked out that, yes, that really was what was going on there. So that was a piece of good evidence for the discreteness of matter. Well, meanwhile, Einstein's third paper was about the photoelectric effect. So the photoelectric effect had been observed that if you shine ultraviolet light on certain metals, you would get an electric current. You get, so it's sort of as if, oh, by the way, another important piece of this picture, 1897, J.J. Thomson discovers the electron, discovers that electricity is made of discrete particles, and that you can get, for example, you can make a cathode ray tube where you're streaming these electrical particles through the vacuum, and they're sort of landing on a screen which can get illuminated. That's how old televisions, oscilloscopes, computer displays used to work. Well, so 1897, electricity is discrete. 1900, kind of this, well, you could have some sort of, the implication was you could have some sort of discreteness in the electromagnetic field. And meanwhile, from Brownian motion, it's like molecules seem to be discrete. Okay, so then 1905, Einstein is trying to figure out the photoelectric effect and says, well, one way that you could have the photoelectric effect is if there were photons, if there were discrete particles of light, and that the photoelectric effect was a particle of light kicks an electron, a particle of electricity, out of wherever it was and makes it a piece of electric current that is a moving electron, moving piece of electricity. And so from that, he then noticed that if you took Planck's constant, found from fitting blackbody radiation, and you took the frequency of the light that was the ultraviolet light that was causing the photoelectric effect, that, well, if E, the energy of the photon, was equal to H times the frequency, nu usually, if E equals H nu, then you could explain the photoelectric effect. In other words, that there was this relationship that used the very same constant that Planck had identified in the blackbody spectrum, and used it, and the interpretation, which would then fit with the blackbody spectrum, was exactly that there were particles of light, and that there was a discrete, that there was a kind of each particle of light had an energy that was associated with its frequency. So that was kind of the origin of photons, and Einstein's paper about the subject really starts in a very philosophical way, saying we know about the electromagnetic field. We now know that that matter is discrete with atoms from things like Brownian motion. We now know that electricity is discrete. So why don't we imagine that the electromagnetic field will also be discrete? Does that work? Well, look, we have this stuff from Planck and so on. So that was that. Okay, there was another thing going on, which was about atomic spectra. So people had observed that different things like gases, for example, if you heated them up, they would emit light at particular frequencies. And similarly, if they were absorbing light, they would absorb light at particular frequencies. It was as if somehow there was something discrete about the way that light was emitted or absorbed by the material, atoms, in things like gases. So atomic spectra have been observed. The fact that there were these discrete spectral lines, there were these discrete, in hydrogen, for example, you can have a situation where you will have emission from hydrogen that is at this frequency, that frequency, that frequency. It happens that in hydrogen, the main sort of series goes roughly like 1 over n squared, but there's and then it's all the differences between 1 over n squared for every value of n. Those are the different spectral lines that show up in hydrogen. Okay, so people had seen that. It's like, why does that happen that way? Well, the other question was, well, what are atoms made of? We have this idea there are discrete atoms. We now know there are electrons. What else? What's in atoms? So the next big thing that was discovered was Ernest Rutherford discovered the atomic nucleus. And so what he was doing, well, okay, there was a different piece, which was the discovery of radioactivity, and by people like Marie Curie and so on, Becquerel, discovered, this was around the 1890s, discovered that there were, that you would get that something like radium was radioactive. That is, that you start with radium, and after a while, you have a different chemical element. It had been sort of thought that chemical elements were, once you have that element, you were done. It would never change into another element. I mean, back when the alchemists were in business in the Middle Ages and so on, the big goal had been to convert lead into gold, to turn one element, lead, into another element, gold. That kind of fell into deep disrepute, and people thought elements are forever, so to speak. And then radioactivity was discovered. It was discovered that an element like radium could decay into other elements after a certain amount of time. So radioactivity was known, and there were these, that caused one to know that there were these radioactive particles. There were these particles that were emitted when there was radioactivity: alpha particles, beta particles, gamma particles. Alpha particles turn out to be helium nuclei. Beta particles turn out to be electrons. And gamma particles turn out to be photons. But anyway, so Rutherford had alpha particles, which he got from a radioactive source. And then he tried to, he could concentrate the alpha particles so they were all going in a straight line. You could do that with an electric field. That's how cathode ray tubes worked with electrons and so on. But he did that with alpha particles. And he kind of, sort of ran them through a gas. And what he found was most of the time the alpha particles just go straight through. But occasionally the alpha particles were scattered at a large angle. And so the question was, why was that happening? And what Rutherford figured out is that's because there's a hard bit inside the atoms, the nucleus. And when the alpha particle hits the nucleus, it's sort of momentum conservation causes it's scattered through a large angle. Otherwise, it's just going through sort of more or less empty space in the atom. So that led to the idea that, well, there were electrons in atoms and there was a nucleus in atoms. And the thing that was different between different elements was the structure of the nucleus, number of protons, and so on. Protons weren't yet known, but that was, let's see, that was then was sort of the question, well, what are atoms like? And there were the kind of these jelly models of atoms where they were kind of like, well, there was an atom and there were sort of electrons that were stuck in this kind of jelly that formed the atom. Thomson had a model of the atom that was like that. Okay, well then along came Niels Bohr, who was kind of a creative Danish physicist, and he had this other model of the atom in which he said that, well, actually there is the nucleus and then there are sort of electrons around the nucleus, and there were certain rules, he said, for certain discrete states of the electrons. He had that idea of discrete states for the electrons to explain atomic spectra, because atomic spectra had these discrete lines. And the question was, what was leading to those discrete lines? And he said, well, it's because the electrons in an atom can only be in discrete states. And those discrete states, for example, for the hydrogen atom, this lineup of these discrete states, and it's because you're seeing transitions between those discrete states that you see the spectral lines that you see. Didn't really explain why there were these discrete states, but he invented a bunch of rules for what the discrete states might be. So that was sort of the next stage. Then the question was, well, why are there these discrete states? What's going on there? And that's when we get to 1925, I think, and Erwin Schrödinger and Werner Heisenberg a little bit later. But Schrödinger had this idea, well, what if these electrons have what he called a wave function? And what if, in fact, what's going on is that inside an atom, he said, well, how do you get discrete stuff out of something where there's just sort of electrons hanging out somewhere? Well, he said, well, here's an example of something discrete that you get. If you have a string that you can pluck and you've got it locked at the two ends, you can have a string that is bowed once in the middle, that bowed twice, bowed three times. You have the modes of the string. You have the harmonics associated with the playing of the string, and there are a discrete set of these. It's discrete in the sense that there's you can just have sort of one hump, two humps, three humps, and so on. So maybe that's what's going on in atoms with electrons, that you're kind of seeing discreteness because there's a wave function that is continuous, but you're seeing these particular modes of the wave function because you have essentially these boundary conditions that are locking it to have to be in this form or that form. And so that was Schrodinger's idea. And he came up with an equation to describe how the wave function would behave. It's a particular form of equation. And that equation, when you kind of say, well, what would that equation? It involves a potential. That means the sort of a force term associated with, for example, an electric field, as we might expect would exist in an atom if there was a charged nucleus and so on. Electrons we know are charged. And so then he worked out, given that, he worked out what would an atom be like. And turns out it fit what atoms were thought to be like. Well, meanwhile, that was sort of an interpretation involving wave functions and so on. Werner Heisenberg came up with a thing he called matrix mechanics. And matrix mechanics was a little bit more directly, let's look at the states of an atom. Let's just look at these things which correspond to the electron in this state, that state, that state. And let's have those be kind of the elements of a vector. We say it's in this state or it's in that state. And then we say there are sort of transitions between these states that are associated with matrices. And that turned out there was sort of a formalism for, okay, well, you apply this matrix and you keep applying it, and there's sort of an equation that describes it. It's a continuous differential equation again that describes the application of this. Well, for a while, there was sort of this question of, well, should you think about it in terms of Schrodinger's wave mechanics or Heisenberg's matrix mechanics? It became clear quite quickly that they were equivalent. They're just two different versions of sort of the same story. But there was this idea of a wave function, and that idea of a wave function was where you would observe only certain features of the wave function. You would observe these, oh, is it in this state where it's one hump, two humps, whatever? That was represented in matrix mechanics in a slightly more direct way. But this idea arose that quantum mechanics is about the story of these discrete states, and that underneath quantum mechanics was sort of this continuous Schrodinger equation thing that was made discrete in the same way that the modes of a string are made discrete. So, but then, well, then there was a question of, well, what does the wave function on its own mean? And what, for example, if you're not in a hydrogen atom where there are these discrete states, but you're, for example, doing a scattering experiment where things are sometimes reflected, sometimes transmitted, and so on, what is the bigger picture of how you can use this wave function? And along came Max Born, and he said, well, why don't we just say that the square of the wave function is the probability? So in other words, you say you do a scattering experiment, you can describe it in terms of the wave function. That's the underlying quantum description. But what we actually observe, for whatever reason, is we do many experiments and we get different results, different times. But the probability to get a particular result, Born said, is the square of the wave function. And why is that? I mean, what usually when you have probabilities of things, you say there's an underlying thing going on. We don't happen to know everything about it. So we end up with only being able to say there's a certain probability. But in this case, it was like there's fundamentally probabilities. And that's the so-called Born interpretation. Well, it's the Copenhagen interpretation, and then the Born rule. The Copenhagen interpretation from Niels Bohr being, at that point, had started the Niels Bohr Institute, which was funded by a beer company in Copenhagen, still exists today. Don't know if the beer company still exists, but the institute still exists. That was sort of a center of the early development of quantum mechanics. And this Copenhagen interpretation, the square of the wave function is probability, and that's kind of and then the Born rule is the specifics of that correspondence. Nobody really understood why it worked that way. Still don't. I think we're beginning to have some idea, but that's so that kind of got quantum mechanics to 1925. Another thing was discovered around that time was electron spin. It was discovered that again in the story of discreteness of things, it was discovered that electrons in atoms, for example, there would be these, you could sort of account for these different energy levels in atoms by how excited the electrons were, how much, whether they were in the lowest mode, like the string thing, or the next mode, and then what their orbital angular momentum was, what essentially kind of, although this isn't really what was going on, sort of how much they were kind of, were they sort of going around the nucleus sort of at one level or at another level, as in how much going aroundness, how much angular momentum was associated with them. But that was also quantized. Then there was the idea that what was seen was there was additional splitting, hyperfine splitting it was called, between different atomic spectra. When people measured these atomic spectra, they noticed there was just lots of atomic spectral lines were broken, or energy levels were broken in two. What was that? Well, it was realized that that was electron spin. It was the spin, was the thing, the electron spin essentially pointed up or down relative to, for example, a magnetic field that the atom was in. And then there was a thing called the Stern-Gerlach experiment that was, I think, 1930-ish, that in which you have beams of electrons, and you notice that in a magnetic field, they're sort of split into the ones that were sort of spin up and the ones that were spin down, and they kind of go into two different clumps. And so that was then realized yet another thing was discrete. The spin of an electron was again discrete. Well, actually at the time, and this is sort of a important topic for me, is people also thought space was discrete, but they couldn't make that work with relativity, and it was sort of an idea that was abandoned. And 100 years later, we brought that idea back to life, and turns out that's discrete too, just like all these other things that turned out to be discrete. So it was kind of a 100-year detour of space being continuous, and now realizing that we actually do have this sort of computation-based formalism that allows us to understand space as discrete. Just to say a little bit more about the history of quantum mechanics, well, in the 1920s, there was things like the uncertainty principle, and kind of the interpretation of quantum mechanics in terms of classical mechanics. Classical mechanics was pretty well developed by that time, and there was a whole set of mathematical methods for dealing with classical mechanics, particularly so-called Lagrangian mechanics, in which you're looking at a mechanical system in terms of its degrees of freedom. So, for example, you might have levers and pulleys and things, and you say the lever is in this position. It has a degree of freedom that says what's its orientation. Or it also has, so it has sort of two important characteristics. Where is it? What is its position? And what is its momentum? Where is it and how fast is it going? And so those became the so-called canonical coordinates that describe mechanical systems, usually denoted P for momentum and Q for position. And there's a whole theory of Lagrangian mechanics that's based on so-called canonical coordinates. And in classical mechanics, there are things called Poisson brackets, which are basically, well, it's roughly PQ plus QP, and it's a way of it's kind of a way of describing Newton's laws of motion in kind of a formal mathematical way that works with these canonical coordinates. So what happened, Heisenberg came up with the idea that you could actually think about sort of generalizing classical mechanics, which had certain ways of combining canonical coordinates, to quantum mechanics, that you would just replace these Poisson brackets by so-called commutators, and that you would get kind of and that was sort of the uncertainty principle. PQ minus QP is equal to I times H bar, where H bar is Planck's constant over 2 pi. And that became the uncertainty principle, which became the story of how you can't simultaneously measure both the position and the momentum, or the energy and the time associated with something. And that was sort of mathematicized in this kind of uncertainty principle idea with commutators and all that kind of thing. Another thing that came at that time was Wolfgang Pauli's exclusion principle that said two electrons can't both be in the same state in an atom. And that was important for explaining kind of how it was the case that, for example, as you put more electrons into atoms, for example, you go through the periodic table where you have elements with progressively more electrons in them, why it was that the subsequent electrons that you put into those atoms had to be in higher energy states. And that's sort of the key thing that leads to chemistry, is the fact that you get these kind of so-called shells of electrons where the electrons are forced to be in higher energy states. That's because of the uncertainty principle, which Pauli came up with, which just sort of asserted that you can't have two electrons in the same state. That was subsequently mathematicized when quantum field theory was developed. Well, actually, with the Schrödinger equation already, you could mathematicize that by talking about if you have the wave functions for different electrons, that you can only have these antisymmetric combinations of wave functions to describe these systems. So another thing that happened, I think this was 1931, if I'm remembering correctly, was maybe 27. I might have my dates off by a few years here. Was Paul Dirac coming up with the Dirac equation. So the Schrödinger equation purported to be an equation that would describe the wave function for quantum particles. But one question was, what happened when those quantum particles were relativistic, were traveling close to the speed of light? Well, that needed another idea, and that other idea was introduced by Dirac, and it's a different form of equation. In the Schrödinger equation, time and space are treated very differently. In the Dirac equation, time and space are treated sort of comparably as they are in the standard formalism of relativity. Dirac equation implied the existence of antimatter, that was, and positrons as well as electrons and so on, just as a matter of the mathematical structure of the equation implied that in addition to there being a wave function for the electron, there must also be a wave function for the anti-electron. And then a few years later, the positron was discovered experimentally from cosmic rays after several other particles had been discovered. But then around the same time, this is now late 1920s, the quantum field theory started to be developed. The question was, if you had, in a Schrödinger equation, you're just describing one particle. And you might say that particle is in a potential field, so to speak. It's like there's an atomic nucleus, it's producing an electric field, the particle is in that electric field, and that was sort of a particle in a potential, was what the Schrödinger equation is really describing. But what if the field itself is quantized? What if you have to describe the aspects of the field itself? And that was what led to quantum field theory. It was a bit of a mess at the beginning. It actually stayed a mess for a long time, because the idea was, if you have in the Schrödinger equation, it's like one wave function for one, there's a psi of x, y, and z or something, and time that represents the wave function for an electron. If you have another electron, it's psi2 and psi3 and so on. You have separate wave functions for each electron. And so you have a system of differential equations. It's a coupled system of differential equations representing the relationship of the wave functions for all those different electrons. Well, what if you have an electromagnetic field where you have photons in that field, but photons can pop in and out of existence? You can change the number of photons. How then do you formulate something like quantum mechanics? And that led to the idea of what's called a Fock space, after a person named Vladimir Fock, a Soviet mathematical physicist. And the idea there is that let's see, the original idea in quantum field theory was the following. Imagine that you can have states that correspond to the one photon state, two photon, three photon, four photon, and so on. You've got all those possible states. And what you're then describing using a matrix mechanics kind of idea is what the occupation number in each state is. So you say there are those states, they in principle exist. There might be nothing in one of those states. The three photon state might just not be present. And to describe the fact that we really mostly have four photons, we say the four photon state exists and has a certain amplitude, and the other photon states have no amplitude. So then we just have a four photon state. Well, so the idea was that quantum field theory became a description of how these different sort of modes of the quantum field with different numbers of quanta in them, different numbers of photons, for example, in them, will be related. And there are, so one of the things that happens is there is an uncertainty principle for the number of quanta that you have. And so that's why you have 0-point fluctuations, because you can't know for sure that you really only have 0 quanta. There's always some amount of fluctuation. And this is a longer story. I could perhaps tell this at some point about kind of the foundations of quantum field theory. But one of the things that so quantum field theory was mathematically really complicated, still is. Quantum mechanics, the story of one particle at a time or a few particles at a time, a bit more mathematically understandable, fairly traditional kind of study of differential equations and so on. But there was a lot of question about the interpretation. What did it mean? What did this wave function actually mean? Hence the Copenhagen interpretation and so on. Well, into the middle of all of this came John von Neumann and some other people in the 1930s who decided they would sort of mathematicize this whole story. And they would try and sort of make this notion of, oh, there are these quantum states and there are these measurements that can be done on quantum states, and tried to set it up to be kind of a full mathematical theory. The idea of things called density matrices and so on came in. That was sort of a way of combining quantum states. The idea of states, superpositions of eigenstates. The eigenstates are these kind of modes like the one hump, two hump, three hump kind of thing from the Schrodinger equation. How do you have something which is a superposition of multiple ones of those different eigenstates? And there was a whole sort of mathematical theory developed about this. So that was a perfectly successful mathematical theory. By the 1940s, there were all kinds of issues with quantum field theory and with working out things in quantum field theory, particularly quantum electrodynamics, the theory of electrons and photons. And that was, there were a bunch of problems with infinities where you would calculate the effective mass of the electron based on its interactions with photons, and oops, it's infinity. That already existed in classical electrodynamics by having an electric potential that was proportional to 1 over r, the radius. And if the radius of the electron was 0, which is what one was assuming, then that would be infinity. That kind of phenomenon has a different version, but occurs again in quantum field theory and in quantum electrodynamics. That problem was kind of swept under the rug successfully by my friend Dick Feynman in the 1940s, late 1940s, 1948 maybe, by the idea of renormalization. We can talk about that separately. Dick Feynman never really believed in that. He always thought it was a sweeping the problem under the rug, which it is, but it's a good sort of philosophical way of thinking about it. Anyway, and then along with that, the idea of Feynman diagrams, the idea of being able to compute things in quantum field theory, that showed up. Lots of other things developed. We can talk about that perhaps if people are interested. That's going into the later history of quantum mechanics and quantum ideas. Really, by the 1980s, the sort of formalism of quantum mechanics was, well developed, and it was mathematicized and so on. Sort of philosophically, it was still a bit of a mess. What was this probability? How intrinsic was probability in quantum mechanics? What was sort of phenomena that you couldn't explain on the basis of there being some underlying reality and so on? It all got rather confusing. Then into the middle of that, and again, I can talk about the history of that because I was involved in it. In the early 1980s, kind of the things that became quantum computing started off, and there was sort of, let's take the idealizations of kind of the theory of quantum mechanics and let's kind of build on those, and let's think about doing computation on the basis of those mathematical representations and idealizations. And that's what led to sort of quantum computing, quantum information, and so on. Still didn't really resolve the underlying kind of questions about how does quantum mechanics really work? What's the real mechanism? What's the mechanics of quantum mechanics, so to speak? I think finally our physics project, last few years, we actually do have an understanding of something about what the mechanics of quantum mechanics is. It's not, the I's are not dotted, the T's are not crossed. There's much to still figure out, But I think conceptually we sort of understand how that all works. And it really depends on yet more discreteness of space, discreteness of the paths of history for the universe. That, in the end, is giving one sort of an understanding of quantum mechanics, but maybe that's for another time.